So I'm going to be talking about some recent results with some of my students and my co-authors. These are Andrei Grutka, Tim Morris, Mohammed Sajid, Andrew Russo, Zach Weller-Davies, and Barbara Skoda. I will mostly, I'll try and get at the renormalization part of it relatively, I'll try and get there. But feel free to interrupt me with lots of questions because it's a bit kind of outside. Good, so the fundamental question I'm interested in is we have these two frameworks for physics. One is quantum mechanics, the other is classical mechanics. They have a very similar form. This is the Heisenberg equation for the evolution of a quantum state sigma. This is the Liouville equation for a phase space density rho. And we can imagine having a classical system and a quantum system. So we have a point in phase space, that's the classical system, Q and P. Here it is. This is a very bad drawing. This is meant to be a two-level system. This is the quantum system. So we can imagine a qubit, and we want to know, can these two systems interact? And I'm not interested in the question of, well, I am interested in, but we know how to deal with the fact when a classical system acts on a quantum system, because we do that all the time, like a particle in a potential. I'm interested in the back reaction, so a quantum system back reacting on a classical system. And I could be interested in this because I'm interested in doing thermodynamics or quantum chemistry, but I'm here because I'm interested in this because I'm interested in understanding gravity. And I might be interested in this as an effective theory, like when I'm, say, in cosmology, and I want to study vacuum fluctuations and how they seed structure formation. I might want to treat my background classically. But I might also be interested in it as a fundamental theory, and to be honest, I'm sometimes not sure if I understand the difference in gravity between an effective and a fundamental theory. And that's because gravity is geometry, and so when I think about what I should do as a physicist, I say, okay, I want to pick a Cauchy surface. How do I do that? I need to know the metric. I pick my initial data. In order to know what my initial hypersurface is, I need to know the metric. And then I evolve that forward in time. If I'm going to define my quantum fields in the space-time, then I'm going to, they're going to vanish if the 2 points x and y are space-like separated, and I don't know if they're space-like separated. I don't even know how to impose the commutation relations. And so just the kind of act of doing physics to me feels like what we do is we have a classical notion of time, and it kind of evolves in a particular, in a particular rate in different points in space. And that's how I do physics, and I don't know how to do it another way. In ADS-TFT, I guess you have this background, so you can kind of relate everything to a classical space-time on the boundary, which you know the causal structure of, so you guys are cheating. But that is one way you could imagine doing it, but like in general space-times, I just don't know what I would do at all in order to define quantum mechanics. So I feel like somehow when I do quantum theory, I need this classical background in order to define what I mean by quantum. That's part of the motivation. And so if we want to think about gravity, I guess what I want to say is gravity is not a gauge theory. So gravity is special. It's different to the other forces in nature. It is geometry. Yes? I'm not at all ruling that out. I'm exploring an alternative. Okay. And the best odds I've got on a bet are like 5,000 to 1. So take this with a thing. But the first thing I want to argue is that gravity is different to gauge theories, and so it's not unreasonable, given that gravity is the only theory which has a universal background geometry, that it is different to the other forces. Or it's not even a force, is it? I mean, it's not a force. It's just geometry. Particles follow geodesics. So it's not even a force. There's no reason, well, not saying there's no reason, but it's not clear that we should treat it as we do the forces. And it's not clear that if it's describable by geometry, that we should describe it in terms of gauge bosons. Maybe, but maybe not. Okay. Questions? People want to fight? You can ask questions. I'm happy to. Okay. Good. Okay. So, gauge transformations act on fields at a particular point. Diffeomorphisms, which is the active part of coordinate transformation, it moves the points themselves, so it doesn't act on the fields, it moves the points. So GR is not a gauge theory. The Wheeler-DeWitt equation, if I try and quantize, because of diffeomorphism, if I want to quantize gravity, I have the Wheeler-DeWitt equation. That causes all kinds of problems, like, well, we've discussed some of them, like, maybe I can measure on the boundary and collapse some poor person in the middle into some eigenstate of the Hamiltonian and really mess up their lives from far away. So there's various things about gravity that keep me up at night, and so I want to consider this alternative. Also, gravity is not renormalizable, and this theory, at least the pure gravity theory, is. Questions about the motivation? Yeah. This is gravity is not a force, it's the arena in which matter lives and acts. Something like that. Okay, so, huge if true. So if it was true that we should treat space-time as fundamentally classical, then I think there's a number of nice implications which follow. So one is, it's, as I said, formally renormalizable. The black hole information problem, information gets destroyed, we'll find out in this theory, so I will not be kept awake at night wondering about state dependence because information just gets destroyed. It has this feature which we don't fully understand, but it seems that it does have changes the gravitational field, both in cosmology and on the galactic scale. It's possible, we don't know how big this effect is, but it has the potential to either be another explanation for dark matter, or it also could be a way to test the theory experimentally through observation. We don't need the Born rule, that's exciting. So the wave function just collapses when it interacts with classical space-time. And these are also testable, this theory is testable on tabletop experiments. So we are trying to do these things. So that's the motivation. There's been a big debate over the years, but it is true. You can construct consistent dynamics, which is classical, which combines classical and quantum systems. In fact, these things have been known. There's been simple examples since the 90s, mid-90s. And in these examples, quantum mechanics is linear. So when people talk about the semi-classical Einstein equation, where you take an expectation value of Einstein's equation, we will not be doing that. I'm going to repeat, we will not be doing the semi-classical gravity because that is nonlinear and therefore inconsistent, but we will be able to find a consistent, some consistent dynamics which consistently couples classical and quantum systems. Okay. So the plan of the talk is I will discuss the general form of the dynamics through a path integral because I know many of you love path integrals. And then I will talk about the experimental tests that you can do to test the theory, and then I will talk about why the theory is renormalizable without ghosts, and the quick answer is it has higher derivative terms, but, so it's formally similar to something called quadratic gravity, but, and the big but is, higher derivative theories can be pathological. They have negative norms, or ghosts, or tachyons. This theory does not have those things because it is a classical theory. So that's the kind of the punchline, so that you don't have to listen to the rest of the talk. Okay, so the framework again, we have a quantum system, we have a classical system, point in phase space, quantum system lives in a Hilbert space, and now we want to describe the joint state of the system. So what that means is that for every point in phase space, we have a quantum state. We can also describe it as a density matrix, so a 2x2 density matrix here for a qubit. So conditioned on where it is in phase space, it will have a different state. So conditioned on it being at this point Q, it has a probability of being 0, a probability of being 1, and then some coherences. And it also just has a probability distribution over where it is in phase space. Okay. And for those of you in quantum information, just like the classical phase space, the probability density and the density matrix, this classical quantum state is positive and it has to be normalized. And so consistent dynamics is just going to be that it be a linear map which preserves the state space, and that will give consistent dynamics. So just like how people derive the Lindblad equation if you're in quantum information theory, or derive the Fokker-Planck equation if you are in statistical physics, you can turn similar machinery and show that there's only, you can derive the most general form of dynamics which preserves state space.
So it's not rho of Q and P multiplied with sigma. On the previous slide, I think.
Oh, in the previous slide. Well, you can write them like this. That is not a great way to write them. So
This is, yeah, so you have both, everything depends on Q and P.
Yeah, sorry?
Yeah, so both things depend on Q and P is the question.
Yeah, that's not a great way. Yeah, exactly. Both of those things depend on Q. So this is like the probability of being at a particular point in Q, and then there's a given density matrix at that point.
So you could just think of a single matrix.
Yeah.
What's the point of multiplying the rho?
Yeah, so I sometimes write it like this. That's maybe an easier way to think about it. But you still have a probability out there of actually being at that point in.
That's the tracing.
Yeah, exactly. And so I will just quickly give a simple example of a Stern-Gerlach. You have the Hamiltonian, a free particle, p squared over 2m, so it lives in phase space. And then I have a magnetic field with a spin sigma. So I'm going to measure the spin with a magnetic field, and the particle will go up or down, depending on whether the spin is up or down. I can start it in the plus state. And there's a kind of remarkable thing that happens, which is partly why I'm interested in this theory, to use it to understand the black hole information problem. And the amazing thing that happens is that the quantum state stays pure, conditioned on the classical system. So there's a breakdown in predictability, but there's no loss of quantum information here. The quantum state stays pure, but there's a breakdown in predictability because the classical particle will jiggle around, but there's no loss of quantum information. So in the Stern-Gerlach case, you start in the plus state, you will either collapse into the 0 state or you'll collapse in the 1 state, but the whole time you stay on the surface of the Bloch sphere, meaning your quantum state stays pure. And you can see that there has to be randomness in the classical field here, the classical particle, because if there wasn't, you'd instantaneously be able to tell if you were up or down. So the fact that there is randomness in the classical system means that you are able to have coherent superpositions of states. So here is the dynamics. I've written it down, all of it, for the master equation. You have this part, which looks like the Heisenberg equation for quantum theory. This part, which looks like the Liouville equation, but it's got an operator ordering ambiguity, so you take both of them, and then you have a diffusion term and a Lindbladian term. Are there questions about the dynamics? I've gone through it quickly, but that's because I want to get to the renormalization and the path integral. That's the master equation. So you can describe the dynamics with the master equation, or you can describe it with the path integral. Just like in quantum mechanics, I can describe dynamics via the Heisenberg equation, or I can use the path integral. Yes?
So there's the Poisson bracket and the commutator period.
That's right.
I kind of missed that. You probably explained that before, but
Sorry, say that
how
again?
can you have both a commutator and a Poisson bracket simultaneously?
This is quantum field theory in curved space. So this is like, there's a Hamiltonian, so this is the commutator, so it can depend on Q and P. So just like quantum field theory in curved space, we have quantum evolution, but the quantum evolution depends on the classical degrees of freedom, which is the metric in that case. So this is quantum, this is the classical system influences the quantum system. So this is like quantum field theory in curved space. And then this is the Poisson bracket. And this is like the back reaction term. And you're asking, how can I have both of them? Well, you always have both of them, because imagine I have a Poisson bracket which has many degrees of freedom, like the Q1 and the Q2 and the Q3. I would have many Poisson brackets, right? I sum them for all the different degrees of freedom. And so just like I have a sum, if I had two systems which are both classical, I would have two Poisson brackets, one for the Q1, one for the Q2. If I had two quantum systems, I'd have two, and there wasn't an interaction, I would have, for each system, I would have
But sorry for the specific Stern-Gerlach case. What was the classical sort of part of the phase space, and what was quantum? Did you treat P classically? And
yeah, so here it is. So
quantum?
let's take h p squared over 2m, and then here's the interaction. So this part is just, you know,
It's just a 2-qubit.
Yeah, it's just a qubit in a magnetic field. Then this is the back reaction. So this is what's pushing, with the spin up, it pushes in one direction. This is the back reaction term. And then it has some diffusion and some, so this is like the Fokker-Planck term. This is like the Lindblad term. But remarkably, even though you have a Lindblad term, which usually you think of as decoherence, the quantum state stays pure.
You need an inequality or an equality for the map to be positive?
So for the map to be positive, good question. For the map to be positive, you need, for the dynamics to be completely positive trace preserving, which means probabilities are conserved, or you know, you preserve the fact that probabilities are positive, you need an inequality. If it's saturated, that's when the pure state stays pure.
I see.
And in the path integral, we can only prove that the path integral is positive and renormalizable when the equality is saturated. So saturating the inequality seems special. It means no loss of information, I think, is when you saturate the equalities.
Is there an intuitive explanation for why this saturation results in the pure state? You're balancing the stochasticity just right with the diffusion?
Yeah, I can show you in the path integral. What it means in the path integral is that you had, so you had a whole bunch of Lindblad terms which had an interaction left field acting on the right field, the sandwich terms. So you know in the Lindblad you have the term which is operator acting on the left and operator acting on the right. Those disappear. And so the path integral breaks down into just an action for the, so it's just the cancellation where those things go, and so you just have the bra field evolving freely and the ket field evolving freely. But when we found this, like, it actually did blow our minds. Like, we were not expecting this. No, you need the Feynman-Vernon term there. You need, yeah, that's what's so weird about it. You need the Feynman-Vernon term there. You need the no event term to be there in particular and contribute. It's just that the jump term goes away.
Why this is completely positive trace preserving? Usually you would have thought that the Poisson bracket term would just spoil your, I don't know, trace preserving dynamics or completely positive trace preserving dynamics.
That's right. So Boucher and Trashin, in gravity, Boucher and Trashin introduced this term into the gravity community. It's called the Alexandrov-Gerasimov bracket. So they introduced this, and then them and some other people noticed that the dynamics was not positive. And I think Tadashi and some other people, Blanchard and Jacek, kind of, you know, realized that you needed to add some other terms. So that was kind of the history. You can kind of see that you need something else. I guess one way of thinking about it is that if you didn't have, well, I'll show you actually when we go to the experiment, because maybe that will make it clear.
Question,
Yes.
like, so the equality is like fluctuation dissipation, is it? Or
Sorry?
the equality of this equality is like fluctuation dissipation relation, or
Is a what relation? Is a...
the fluctuation dissipation relation?
Oh, a lot of people ask me that, and I don't know the answer to that.
So I'm wondering, like, if equality is that, like, what is the inequality again? Maybe this is the same question, but
Yeah, so I'll maybe try and get an impression of it from when we get it to the experiment, but I don't know the answer in terms of, I've thought about it a little bit, and I haven't seen that it is, but in my...
fluctuation dissipation is not an inequality, right? It's an equality.
Yeah,
so.
no, I understand.
Okay.
Yeah. I mean, I think it's a bit like, if you go it in one direction, you know, you kind of have too much, if it's not saturated, it's like you've kind of got a hidden environment in the quantum system. You can think of it like that. So you can always, in some sense, purify the rest of it onto a classical system. You could imagine it like that. Any more questions? Okay, so now I'm just going to quickly so if you're more comfortable with path integrals as opposed to master equations, I will give you a sense of it. And I actually just like both of these formalisms because I like seeing the structural, it's taught me a lot about classical mechanics and quantum mechanics and how similar they are. And how, and so I've learned a lot in this project with that. So I guess I want to kind of convey how similar the formalism is for quantum mechanics and classical mechanics. I want to do it through the path integral. I've already done it through you can see the formal similarity already from the master equation. So here it is from the path integral. So the path integral, we have a bra, we were computing an amplitude, so we have a ket going to a bra, and then we sum over all paths weighted by the action. That is the path integral for quantum mechanics. Now I want to compute not just an amplitude, but I want to compute a probability. And there's lots of people here that look at these evolutions of density matrix, these open quantum systems. So I want to consider an initial state here, and I want to know what the density matrix is, so I evolve it in one direction. This is the ket field, and this is or the other way around, the ket field here. And so I'm doubling the number of degrees of freedom in some sense, because I'm going from a wave function to a density matrix. So I have rows and columns, not just a column vector. So I want to have the rows and the columns, so I have two fields. And so this is the path integral for a density matrix. And those of you who know the words Schwinger-Keldysh, this will be familiar, or Feynman-Vernon, this will be familiar. So this is a Feynman-Vernon or a Schwinger-Keldysh path integral. If anyone knows what the difference is between them, I'd love to know. Okay, so that's an evolution of the density matrix and now let us add the Feynman-Vernon term. So this is a decoherence term. It's like the Lindbladian. And we can add decoherence if we're doing the path integral for an open quantum system, a quantum system that has an environment. So here is a nice term for a scalar field. So what this does is it suppresses terms where the bra field is different to the ket field. And this is 0 when the bra field equals the ket field. So on the diagonal of the density matrix, this does nothing. But for the off diagonal, we get exponential suppression. So this is a decoherence term. You need to look at that for a bit before you see it. Any questions? Okay, so this is quantum mechanics for open quantum systems. Now the path integral for classical mechanics is very boring. It's just a delta function around Hamilton's equations. There's only one path. We can sum over all of them, but only one of them counts, okay? So that is a pretty boring path integral. But if we have stochastic dynamics, like Brownian motion, then we have what's called the Onsager-matched loop path integral. And so what it looks like is when you have F equals ma over here, and so when Newton's equation, the force law. So we have F equals ma, and if F equals ma, then that path has the highest probability, but you are allowed to have fluctuations away from F equals ma. That's like Brownian motion, right? We're allowed to have little stochastic fluctuations away from the force. So the force is it's like a fluctuating force. That's like Brownian motion, so this is the path integral from Brownian motion. You can look it up in Feynman and Hibbs, chapter 12.6. And I say that because I refer people to it a lot, because notice here there is a higher derivative term, okay? This is the common path integral for Brownian motion, mq double dot and a square. It's a higher derivative term, like in quadratic gravity, but it's a standard path integral for Brownian motion. So we don't need to panic because we see higher derivatives in this action. Yes? Questions? Maybe I'll show it again. So this would be,
is equal to P, and then P dot is equal to some function of Q.
This is how you would have normally, this is how we're used to seeing it as physicists. So you would have seen it as a Langevin equation. More properly, people do some Ito formalism, but it looks like this, right? The acceleration is equal to some force plus a random fluctuating noise, right? That's Brownian motion, or this is the Langevin equation. So the acceleration has some random fluctuations to it, like it's getting stochastic kicks. And on expectation, the kicks are 0, but they have some 2-point function, so they have some variance. And this variance, the larger the variance, the larger the fluctuations we get away from F equals ma. And So this is called the diffusion coefficient. And if you take the Langevin equation and write it as a path integral, this is what you get. You get the action which looks like F equals ma, and it's squared, and so any deviations away from this are suppressed. Yeah, you can do it. Yeah, you could. I mean, I can also do it like p dot minus f squared. So I could do a path integral that looks like this. That's right. Yeah. So this actually has a different name. It's like Schwinger-Keldysh and Feynman-Vernon. This is called well, in the field theory case, this is like Martin-Sigia-Rose formalism. But for some reason, there's a different name. So you can do it in either, the phase space formalism or
the way you split up boundary conditions unique or something, like you have to always place these three initially and one in the future, or like, is that unique?
Sorry, can you repeat the question? Okay.
The boundary conditions you give for the path integral, is that the way you split up between future and past, is that unique or?
Yeah, so the boundary conditions are interesting actually. So when you have a stochastic path integral, and this is one of the other strange things, is that you kind of have another degree of freedom. Because now, before you just would say what Q and, you would say what Q and Q dot were initially, but now because you have you get like Q double dot becomes a new degree of freedom in some sense. And so you get these additional degrees of freedom, which in the case of, the gravity theory means that you have a scalar mode now as well. So in addition to the tensor mode, you now have scalar, because the Newtonian potential is now, it's no longer just a constraint, it's no longer constrained by the matter, it's now a degree of freedom because it's fluctuating. Okay, so that explains a little bit why in quadratic gravity, you got these additional degrees of freedom, which are very useful, for example, like in Starobinsky inflation, which is favored by the data. You have this additional scalar field, and here we see it arising as a stochastic fluctuation.
Asking, is the splitting which you did, like one Q at the future and the three things in the past, could have as well done QI dot and QF QF dot?
You can do whatever you want, right? Like I can condition, I mean, just like the path integral.
Are they all unique solution giving boundary conditions? That's what I meant, I think.
It'll be a probability given so it's a probability given some boundary conditions. But I guess I would, if I don't specify, I think this is true for this one, that you need to specify these 3 degrees of freedom, and then you will get a unique probability distribution. But if you don't specify the acceleration, then you might not. Sorry, I didn't understand the question, but I do now. Okay. So now for gravity, remember what we did was we had an equation of motion squared. So we're going to try to do some equation of motion squared. So here's the vacuum gravity. We have Einstein's equation squared. It's a little bit, we have to contract tensors for that. There's different ways we can contract it. And so what we, okay, so yeah, so I'll just say for gravity, we can try and contract the tensors. We're going to get these higher derivative terms like R mu nu, etc., which you see in quadratic gravity. Are we for time? Okay. So here are the different path integrals. I said I would show you kind of how formally similar they were. You have in quantum mechanics, you have, this is kind of a general path integral where you have this Feynman-Vernon term for decoherence. In classical stochastic dynamics, you have this Onsager match loop path integral where you have, Hamilton's equation, but you allow for fluctuations away from Hamilton's equation. And then the way you can combine them is that instead of sourcing them by, for example, H di Q, you source them from both the bra field and the and the Ket field. And that's very similar to the master equation that I gave you there, where you have an operator order ambiguity, and so you get sourced by both things. And you can show that this thing is positive semi-definite. Oh, okay. Okay, well, let me do the experiment first, and then I'll quickly go back to the quadratic gravity renormalizability thing. So let me just explain the experiment and why and y for the experiment, how we can test this, and why it kind of gives you, in some sense, you don't need the measurement postulate. So we start off in a superposition of a test particle here and there. We turn on gravity. And so now, if the geometry of spacetime is classical, then we can measure whether the particle is here or there by measuring the gravitational field. And since we can measure the geometry to arbitrary accuracy, we should be able to collapse the state right away and find out immediately whether it's here or there, because we can measure the gravitational field perfectly accurately. We will collapse the state. And because of that, we would violate the uncertainty principle, right? Because we could also imagine that someone measures the momentum at the same time. And this is a manifestation of the dynamics not being completely positive, actually. So what you find is that in order to be completely positive, you have to have some sort of stochastic behavior, so some noise. So the gravitational field now has to have lots of little stochastic fluctuations in order for the dynamics to be completely positive. And so if you're trying to measure the gravitational field to find whether the particle is here or there, you won't be able to, because there's all these fluctuations and it doesn't unambiguously determine whether the particle is here or there. And so we can imagine measuring the gravitational field, measuring the gravitational field, measuring the gravitational field, until eventually we learn enough from the gravitational field that we know that the particle is there. So that is how why it causes particles to localize. But I want to emphasize that the wave function of the particle, even though it was in a superposition of here and there and eventually collapsed to being there, the wave function stays pure the whole time, conditioned on the gravitational field. So it's a very strange sort of a collapse. It more just kind of rotates. So one of the things I've learned in this project is that they're very similar. So a classical stochastic field looks very similar to a quantum field. Certainly it's different because I can violate a Bell's inequality with a classical field, which I can't do with a quantum field. So it's different. There's no entanglement. There's a restricted set of states, and the path integral has to be completely positive. So there's a lot of restrictions, but a lot of the things that people associate with quantum field theory, like huge fluctuations at short distances, well, classical stochastic fields have the same property, and that's why you have to renormalize them. So that's effectively the experiment, is what I just mentioned, which is that so as I mentioned, that eventually, if there's not a lot of stochasticity, you will eventually learn whether the particle is here or there. And so we would know, for example, if particles that are massive can remain in superposition forever, then the gravitational field, if it's classical, would have to be incredibly stochastic, such that we would never learn where it is. So there is a trade-off, this we call the decoherence diffusion trade-off. There is a trade-off between how much coherence a particle can maintain in, say, a double slit experiment, versus how much noise you have in the gravitational field, which you need a lot of noise in order to have particles be very coherent. And so we can combine these two experiments, and potentially we could, for example, if we find that we don't see this noise in the gravitational field, we would rule out any theory in which gravity is classical. Because you can prove that this trade-off between how much noise you have in the gravitational field and how much coherence you have in the quantum field, you can prove that this is a feature of all theories in which one of the fields are classical.
Preserving, but it isn't unitary, right?
That's right, it's not unitary.
I see. Isn't that confusing? Because now you could take an EPR pair and take one of the qubits and have some classical particle attached to it. Now this qubit is not evolving in a unitary way.
Yes.
And that means the density matrix of the other qubit will change. So, somebody on Mars will know, because this didn't evolve unitarily, right? So how could you preserve the density matrix on the other side?
No, so just to be clear, so there's a difference in language sometimes between quantum information and high energy. When I say non-unitary, all I mean is that there's a breakdown in predictability. So you have a breakdown in predictability, just like decoherence is an example of a non-unitary map. So we, of course, know that if we have an entangled particle with another entangled particle, sorry, if we have separated entangled particles, then if this one decoheres, no big deal, right? Like this one stays the same. And that's the same thing here. You have, this one might have some stuff happening to it, but it preserves the density matrix. So this dynamics is local. Yeah.
Interacting with the gravitational field,
Yes.
then linearity as far as the quantum part is concerned is preserved, right, by the dynamics.
Yeah, that's what the demand, that for both the classical, I mean, classical probabilities, we also must be linear in them, because otherwise, the way I put it sometimes is, if your dynamics is not linear, then you will get different dynamics depending on what you would have done had the coin flip being heads instead of tails. So, if you flip a coin and do something, then the dynamics shouldn't depend on what would have happened if you had done something else in the event of another coin flip. So that's what linearity means so here we mean linearity in the density matrix and in the probability density. Okay. But the linearity in terms of the whole thing, because of course you could, conditioned on the classical system, you could do something different on the quantum system.
Okay, thank you.
I mean, this linearity, I guess we were discussing because, state dependence is kind of an example where you don't have a linear interaction. So this is, okay. Good, so we're proposing people do these measurements, and now I guess in the remaining 5 minutes, I will do renormalization. So
sorry, I thought you were going to come to the punchline. Are they doable at all in the lab?
Oh, yeah, so, okay, good. So we have already ruled out one, the non-relativistic model, that's just been ruled out. In fact, so that's gone. There is another theory which is a discrete model, and there are claims that that is ruled out by the Aspelmeyer experiment, but Marcus is not so sure, so we don't know, so that one's still there. But then the relativistic model seems not ruled out at the moment. So, we're still trying to work out how close we are to being able, where we are. So my guess at the moment is that Lisa should be able to rule it out or see the noise, but probably not for tabletop experiments at the moment, but we're not sure because it's a subtle, we're in the middle of the calculations. Yeah, sorry, punchlines are good. Thank you for Good, so renormalization. So remember that what we're doing here, the path integral is like an equation of motion squared. Here's the, this is quantum mechanics. So this is just the path integral for quantum mechanics. And now for the classical system, we have F equals ma all squared. So this is like the Feynman and Hibbs Brownian motion. And here's the main message and the punchline is that if you have higher derivative terms in your action and you're doing Brownian motion, everything is okay. But if you have a higher derivative term and you're doing quantum mechanics, you have a negative norm ghost, so that's a problem. So the kind of headline message is that these higher derivative theories of gravity, if you interpret them as classical stochastic theories, then you don't seem to have this problem. And so this is called the Ostrogodsky instability. It arises because if I have a higher derivative action, then that means the Hamiltonian is unbounded from below. But here, our Hamiltonian is just the ordinary Hamiltonian, but just with noise. So it's a bounded from below Hamiltonian with noise. So we just have the same Hamiltonian bounded from below. But if you were doing quantum mechanics instead of classical stochastic dynamics, then your Hamiltonian would be unbounded from below, and you would have this instability, or this, what they call a ghost. Okay, so that's the headline message. So here's the action. You're contracting R with itself, and you have these higher curvature terms. You can write it like this, where you have an R squared term, you have the Weil curvature squared term, and you have a Gauss-Bonnet term. And this is the new coupling constant in the theory, and it is dimensionless and runs. There's no explicit, but it's implicit, right? Because you're summing over all paths. So, okay, all geometry, so you need to gauge fix it. So you're summing over all paths, and so you're allowed to have fluctuations which deviate from, say, let's take the vacuum. Sorry?
I mean, is the difference that there is no I?
That's right, it's pure, yeah, it's pure real.
Is that the difference?
That is the difference, and it's a big difference. I mean, it looks harmless enough, but for example, when you compute all the two-point functions, you need to make sure that they're positive definites, because what you're computing here is a probability, so you better not get any imaginary terms. Yeah, so, well, this is the classical theory, so you don't want to have an I, because you're computing a probability distribution. You want to get a positive number out of this thing. So computing the probability distribution of going from one 3 geometry to another, I better get a positive number. If I'm looking at the scalar part, then I better get the correlation function is actually a covariance matrix. I can find out what the variance in acceleration is, and that better be positive, right? Variances are positive.
Yeah, a related question. So the absence of ghosts is related to the fact that there is no I?
Yes.
So it's like saying that if it was an Euclidean path integral, there is no problem with having higher derivative things.
Ooh. No, I wouldn't.
Not.
I wouldn't say that.
Okay.
I mean, I have no idea what it means. I mean, this is a dynamical path integral. It's not. We're not computing the thermal state or anything like that. So I don't think.
No,
you
I
can,
understand.
Yeah. So it looks deceptively like a Euclidean. I mean, it's not. I mean, this is still a Lorentzian, so looks deceptive. You know, it's not really a Euclidean path integral in any way. That's right.
But why not just use the Einstein's action there?
What do you mean?
Because that will also be dominant with the...
Yeah, this is Einstein's equation squared now, right? But because you're contracting indices, you get something like this, and you can eliminate with the Gauss-Bonnet term. So this is, in fact, Einstein equation squared.
I think why don't you write root gr?
Why don't you use the same action?
Sorry?
Just use e to the minus root gr. It's a number. I mean, if you minimize that, you'll get Einstein's equation.
Oh, you want me to write root r and then minimize that thing with an I in front of it? Yeah, so this is actually kind of interesting. So if I have I and I have something, then the deviations are kind of killed because of the fluctuations in I, right? Here you don't have an I because you want, it's a real thing. So how do you kill it? You kill it by the square. I mean, that's just how it works. So it's a kind of interesting way. The equation of motion here is actually when this thing is 0. So it's not that so when you extremize this thing, so you could say the same thing, well, what happens if I extremize this action? And we call this the most probable path. All it tells you is that those are the extremes of the most likely thing to happen, but they're not necessarily the equations of motion. And that's kind of what's behind a little bit of these anomalous contributions, which we claim may look like dark matter or give a contribution which looks like matter, because you get these other contributions to this action.
What's the space of metrics that you path integrate over?
Sorry?
What's the space of metrics that you path integrate over?
Right, well, you have to gauge fix it in order to, you do the usual gauge fixing to make sure that you're doing an integration over geometries.
But does it include singular metrics?
Sorry?
Does it include singular metrics, or is it only smooth metrics? Because the space of smooth metrics has boundaries where the metric degenerates, and your stochastic probability will probably diffuse towards those singular corners, and that you have to then treat somehow. So,
okay, that's not. I mean, that's not something I've thought about. There's a kind of you have to. So you have to make sure that these other terms don't have such problems as well. So what I want to say is this is formally the same. So we could say this is formally renormalizable. We've shown that the scalar part is well behaved, but we have not shown that the tensor mode is. So there are a bunch of questions like that also related to the normalizability that we don't understand. I'm going to end. You're getting up, so I'm going to end.
Maybe I'm going to say we defer all the questions to later, and then let Jonathan conclude in the next 2-3 minutes.
Right. So let me just end with the concluding slide. And then take questions. So what I want to say, we show that this thing is formally renormalizable. But you need to show all these things happen simultaneously. So you need to show that after renormalizing the theory is still CP-TP, because you might have lost it after you do some renormalization prescription. So we've shown that this, for example, holds for the scalar mode, but as I was saying, we haven't shown it for the tensor mode. You also have to, so there's this tension between CP-TP, renormalizability, the theory being covariant, and vacuum stability. So, these things, I feel like there are examples where any pairs of them we can solve, but we have not shown that the theory satisfies all of these at once. So let me just return with the slide, return to the question, is space-time classical? I have no idea. Okay, it could be. And I put the odds much greater than this, I think partly because of the renormalizability, but just, I really have no idea what nature has decided. So the main points are that so if you accept that space-time is classical, here are the consequences. You find that information is lost, but the quantum state remains pure. So the quantum information is not lost. This is experimentally testable. You don't need the measurement postulate. At the very least, this could be an interesting effective theory or as an alternative hypothesis if we're going to be doing experiments on the quantum nature of gravity. So with that, I want to thank you for your attention.
Just one question from Akhil, and then we can continue over tea.
To confirm again, is the whole of the metric classical, or only the Coulomb part or something is classical and the gravitons are still quantum?
Yeah, I think you can show. So I think you can show that if you're if part of the metric has to be classical, it all has to be. And I think that's a bit like there's a big discussion on these entanglement experiments to test the quantum nature of gravity, where there's no gravitons because the Newtonian potential is the constraint. But I think Wald has shown that there as well, if the constraint, if the gravitons are quantized, then so is the Newtonian potential. So for the same reason.
Very quick for the team. If the CMB sees the tensor mode, will you give up?
If the CMB sees the tensor mode, why is that why is that a signature of quantum gravity?
But that's how we normally think of it. It's spin 2 graviton.
Well, this has a spin 2 mode as well. So you need. This is why I think this is a good alternative theory, right? Because you need to compare it to what would a classical theory predict, and this has a tensor mode as well.
No, you
Oh.
don't do that. But it has a physical spin 2.
Okay, over tea. Back at 4:05.